Hello, and welcome to the third video on complex numbers. In this video, I'm going to discuss Euler's formula and the exponential form for complex numbers. So first of all, what is Euler's formula? It is the formula that's shown here on the slide. E to the I theta equals cosine of theta plus I sine of theta. And it is a very mysterious formula when you first see it. I think one of the reasons that people have trouble understanding this is that they don't understand what the definition of e to the I theta is. Now, the left-hand side of this formula says e to the I theta, and that is equal to something in terms of cosine and sine, which you understand just fine for real numbers theta. But what is this exponential of a complex number? Well, we know what the exponential of real numbers are, and the exponential for complex numbers is found by extending the exponential for real numbers to complex numbers, assuming that the exponential satisfies a certain set of differential equations, which are called the Cauchy-Riemann equations. We're not going to get into this topic in this class. It's more advanced, really. It's something you would study in a course on complex analysis of complex numbers. But that is where the definition of e to the I theta comes from. A more basic definition would involve the Taylor series, which is also a more advanced topic. But there are definitions of this exponential for complex numbers, and that's what I want to get across here. We're going to look a bit more about why this formula is true when we discuss differential equations in the next section. And this makes sense because this complex exponential for complex numbers is defined by extending the exponential for real numbers to complex numbers using the fact it satisfies a certain differential equation. Okay, but for the purposes of this course, we're simply going to take this formula, e to the I theta equals cosine of theta plus I sine of theta as given, and we're going to use the fact that we can use the normal properties of the exponential function, that is e to the x, that we're used to for real numbers. Okay, so there's a few specific examples of this formula that we look at. So first of all, if we put theta equal pi, we get on the left-hand side e to the I pi equals cosine of pi, which is -1, plus I sine of pi, which is 0. And so you get this identity, e to the I pi equals -1, sometimes called Euler's identity. People like to make a big deal out of it because it relates e, pi, and -1, and also the complex unit I in one formula. That's a beautiful mathematical formula that relates some of the fundamental constants of mathematics together. The complex conjugate of the e to the I theta is what you get when you change the sign in front of the imaginary part. So you put a negative sign here, and since the sine function is an odd function, you can bring the negative sign inside, and the cosine function is an even function. Cosine of theta equals cosine of negative theta, and so because of that, the complex conjugate of e to the I theta is e to the negative I theta. And so really you can just put the negative sign in front of the I in the exponent there. Cosine of theta minus I sine of theta. All right, and another identity, if we put theta equals 2 pi, because cosine and sine are periodic with period 2 pi, we wouldn't get 1. So e to the 2 pi I equals 1. Cosine of 2 pi equals 1, sine of 2 pi equals 0. Also, e to the 4 pi, 6 pi I, and so on, they all equal 1. Also for negative multiples of 2 pi, e to the -2 pi I equals 1. And so this complex exponential, e to the I theta, repeats whenever you add 2 pi to theta. This is the point here. All right, and finally, let's note that the modulus of e to the I theta is 1. So you can find that by taking the sum of squares of the real and imaginary part. Cosine squared plus sine squared equals 1. Take the square root, that's 1. Alternately, you can use properties of the exponential. So e to the I theta times its complex conjugate, e to the negative I theta, is e to the I theta minus theta, which would be e to the 0, which is 1. And so these complex exponentials, e to the I theta, have modulus 1. So really what we're getting is the set of all complex numbers that are distance 1 from the origin when we use this form e to the I theta. Theta is then the angle between the positive real axis and the complex number. That's the argument in the polar form. Okay, so Euler's formula allows us to relate the complex exponential, e to the I theta and e to the negative I theta, two trigonometric functions. So the top formula here is Euler's formula, and then if we take the complex conjugate, that's the next one here. If we add these two together, simply add the left-hand sides and the right-hand sides, you see that e to the I theta plus e to the negative I theta equals 2 cosine theta. Or if you subtract these two formulas, then you get e to the I theta minus e to the negative I theta equals 2I times sine theta. And so this relates the cosine and sine functions directly to the complex exponentials. So you can write cosine in terms of complex exponentials, e to the I theta and e to the negative I theta. And also we can write sine the same way. So they're related by these two formulas. And so now if we think back to earlier in the unit when we first introduced the hyperbolic trig functions, remember the formulas for the hyperbolic trig functions were these. The hyperbolic cosine is 1/2 e to the x plus e to the negative x. Hyperbolic sine, 1/2 e to the x minus e to the negative x. And now we can clearly see how the regular trig functions are related to the hyperbolic trig functions. So these formulas for cosine and sine we get through Euler's formula relate to the way we define the hyperbolic trig function. Not going to discuss any more about hyperbolic trig functions now, but I wanted to point out the connection here. Okay, so using Euler's formula, we can write any complex number in what we call the exponential form. So first of all, if we have a complex number z, we know it can be written in the polar form already. It's a topic of the last video. And then this cosine of theta plus I sine theta is e to the I theta. That's Euler's formula. And so this complex number z is r, the modulus, times e to the I theta. This is called the exponential form of a complex number. It's really just the polar form in disguise using Euler's formula, where we replace the cosine theta plus I sine theta by e to the I theta. And so just to point out, as in the previous video about the polar form, r in the exponential form is the modulus of z. So to calculate r, you calculate the modulus. And theta is the argument of z, theta in e to the I theta. And so in order to express a complex number in its exponential form, it's the same as expressing it in the polar form. We need to calculate the modulus and the argument. So for example, suppose we had the same complex numbers in the previous video. This is the example that I did in the last video. Z equals 1 minus square root of 3i. We calculated the modulus of this to be 2, and the argument to be negative pi over 3, that's theta. And so the exponential form for this complex number is 2 times e to the negative I pi over 3. And this is 2 is r, and negative pi over 3 is theta. All right, so the exponential form for a complex number allows us to understand what happens with complex numbers when we multiply them or divide them geometrically. And this is very important for getting a deeper understanding of complex numbers. So suppose we have two complex numbers, z1 and z2. They each have exponential forms, r1 e to the I theta 1 and r2 e to the I theta 2. Then we can rearrange this product and get that the modulus of the product of z1 and z2 is the product of the moduli of the individual complex numbers. It's r1 times r2. And the argument of the product is the sum of the arguments of z1 and z2. I should be a bit careful there because remember we require the argument to be between negative pi and pi, and so it's possible theta 1 plus theta 2 might be outside of that interval. You would still get this formula, which is correct, although theta 1 plus theta 2 is not technically the argument, and you have to add a multiple of 2 pi, or subtract a multiple of 2 pi possibly to get what we would call the argument. But still, what we see is that when we multiply complex numbers, we take the product of the moduli and we add the arguments. All right, and we have a similar thing here for division. So we divide z1 by z2, take the quotient. Well, then what we get is we divide the moduli, divide the modulus of z1 by the modulus of z2, and we take the difference of the arguments. So the argument would be theta 1 minus theta 2, or possibly a multiple of 2 pi, either plus or minus 2 pi, theta 1 minus theta 2. All right, and so as an example, let's look at the product and quotient of these two complex numbers, which are already given in the exponential form there. So we have z1 is 2 e to the negative I pi over 3, and z2 is 3 e to the I pi over 2. The product of z1 and z2 is equal to what we get when we multiply the moduli of the two numbers. So 2 times 3 is 6. And then the argument, or possibly the argument plus or minus 2 pi, is e to the I negative pi over 3 plus pi over 2. We add the arguments of the two complex numbers. All right, and so pi over 2 is 3 pi over 6. Pi over 3 is 2 pi over 6. So when we take this difference here of the two angles, we get I pi over 6. All right, so the argument of z1 times z2 is actually pi over 6, and the modulus is 6. All right, what about the quotient of z1 and z2? So let's think z1 divided by z2. And so we have z1 is 2 e to the negative I pi over 3 divided by z2, 3 e to the I pi over 2. All right, and so the modulus of this quotient is going to be the quotient of the moduli, 2/3. And then for the argument, we're going to have e to the I times negative pi over 3 from the numerator here, and then minus pi over 2. And this, when we have e to the I pi over 2 in the denominator, that's e to the negative I pi over 2 in the numerator, minus pi over 2. And so you take negative pi over 3 minus pi over 2, you get negative 5 pi over 6. So this 2/3 e to the I minus I, rather 5 pi over 6. All right, so the modulus of this quotient is 2/3, and the argument is negative 5 pi over 6. That's between negative pi and pi. So this is how we can use the exponential form to multiply and divide complex numbers. If we wanted to find the real and imaginary parts of these products, of course, we would then have to use Euler's formula. We write e to the I pi over 6 as cosine of pi over 6 plus I sine of pi over 6. And then we can calculate those sines and cosines and determine the real and imaginary parts. All right, so this is an example. Euler's formula allows us to find connections between complex numbers and trigonometry, of course. It is itself a connection between complex numbers and trigonometry. And so if we have, for example, de Moivre's theorem, which you probably have seen before, it says that for any integer, cosine of theta plus I sine of theta raised to the n power is cosine of n theta plus I sine of n theta. And then you can work out the trig identities for cosine of n theta by multiplying out the left-hand side. And this really follows from Euler's formula, because you look at Euler's formula, you have cosine of theta plus I sine of theta raised to the nth power. That's the left-hand side here. That's e to the I theta raised to the nth power. And then we use the property of the exponential. It says e to the I theta raised to the nth power is e to the I n theta. And then once again, Euler's formula says that that's cosine of n theta plus I sine of n theta. And that gives us this formula shown in the box, de Moivre's theorem. And so you can work out trig identities, as I said, for cosine of n theta using this by multiplying out the left-hand side. Let me do one example of that. We'll find expressions for cosine of 3 theta and sine of 3 theta. All right, so we have e to the I theta raised to the 3rd power. equals e to the I3 theta. This is a property of the exponential. And this depends on how we define the exponential. So once again, this is actually a bit mysterious here. You have to think that this is actually true, to realize why this part is actually true. It depends on how the complex exponential is defined. But we're going to accept that it's true in this class. So we can use these properties of the exponential even when we're dealing with complex numbers. Okay, and so the left-hand side here by Euler's formula is cosine of theta plus I sine of theta raised to the third power. And the right-hand side is, again by Euler's formula, cosine of 3 theta plus I sine of 3 theta. Okay, and now we want to find identities for cosine of 3 theta and sine of 3 theta. We do that by multiplying out the left-hand side and then taking the real or imaginary parts. The real part is cosine of 3 theta, the imaginary part is sine of 3 theta. So let's multiply out the left-hand side. You can use the binomial theorem to multiply it out. Once you do that, you have cosine cubed of theta, the first term, plus 3 cosine squared of theta times I sine of theta, and then plus 3 cosine of theta times I sine of theta squared, and then finally plus I sine of theta cubed. All right, that's the left-hand side, and the formula tells us this is equal to cosine of 3 theta plus I sine of 3 theta. And so, once again, cosine is going to be the real part of this that we've just multiplied out, and sine is going to be the imaginary part. And so let's simplify in order to identify what are the real and imaginary parts. So on the left-hand side here, let's collect the terms that are real numbers without the I, imaginary unit. We have cosine cubed, that's a real number. And then we have this one, 3 cosine times I squared times sine squared. And the I squared is -1. So this term becomes -3 cosine of theta sine squared of theta. And that is the real part. This term and this term, those are the ones that are real numbers. And then there's 2 terms that are imaginary numbers. So we have 3 cosine squared I sine theta. I'm going to write this all times I. So I times 3 cosine squared theta sine theta. That's this term. And then this term, this has I cubed times sine cubed. And I cubed is -I. So it's negative sine cubed theta. If you're confused about the I cubed, remember I cubed would be I squared times I, and I squared is -1. So -1 times I. Okay, and so this equals, once again, cosine of 3 theta plus I sine of 3 theta. Right, so cosine is the real part, cosine 3 theta is the real part. You take the real part of both sides. You have that cosine cubed of theta minus 3 cosine of theta sine squared of theta equals cosine of 3 theta. All right, that's the real part on the right equals the real part on the left, and then the imaginary parts. On the left we have 3 cosine squared of theta sine of theta. minus sine cubed of theta, and that equals sine of 3 theta. All right, so that's the imaginary part on the right and the imaginary part on the left. Okay, so this is how we can use Euler's formula in order to find trig identities. All right, now let's continue on. Another application of Euler's formula in the exponential form is to find the square roots of numbers, or nth roots of numbers. And so let's look in particular at the cube roots of 1, just as an example. Find all complex numbers that are cube roots of 1. That means complex numbers that when you cube them, you get 1. So if we want to find a complex number z that is a cubed root of 1, that means it's a solution of this equation, z cubed equals 1. All right, and so let's write z in the exponential form. So the exponential form will be the modulus of z, which we write as r times e to the I theta, the argument of z. All right, and so we plug the exponential form into the formula that we need to solve in order to find all the cube roots. You get r e to the I theta cubed equals 1. And this would be then r cubed e to the I 3 theta equals 1. And so now let's look at the modulus and argument of this number. All right, and so first of all, the modulus is going to be r cubed. That will have to equal 1. And so we get r cubed equals 1, and r has to be a positive real number, and so that means that r would have to equal 1. All right, now let's look at the argument. And so here it gets a little bit tricky. So if we just say, well, the argument of e to the I 3 theta has to equal the argument of 1, we would get that 3 theta has to equal 0, theta has to equal 0. However, you have to be careful here because we can write 1 using angles that are outside of the range from negative pi to pi. And so you can write 1 as e to the I 2 pi n, right, for any integer n. Right? N can be 0, 1, 2, 3, or negative integers. And so that means we could have this e to the I 3 theta equals e to the I 2 pi n. We can have 3 theta equals any multiple of 2 pi. So looking at the argument, we'll get a correct answer, well, a z that satisfies this equation, z cubed equals 1, if 3 theta is equal to 2 pi n, and where n is an integer. And so if we divide by 3, we get the theta can be 2 pi divided by 3 times n. Okay, so this gives us an infinite number of possibilities for theta. But actually there's only 3 solutions to z cubed equals 1, 3 cubic roots. We know that for a third degree polynomial there should be 3 solutions. And so really the only 3 values of n give us distinct complex numbers. And this is because when we add 2 pi to theta, we get another complex number, which is the same. That follows from Euler's formula. And so, for example, if we take n equals 0, we get theta equals 0. We already know that that is one possibility. E to the 0th equals 1. We could take theta equal 1. We would then get 2 pi over 3. And if we want to ensure that theta is between negative pi and pi, so it gives the argument of the complex number. We could take the n equal -1. We would then have negative 2 pi over 3 also. So here's three possibilities for theta. If we took, say, n equals 2, we would get 4 pi over 3, and that differs from negative 2 pi over 3 by a factor of 2 pi. So the other values of n would differ from one of these by a factor of 2 pi. So that means that these are all the possibilities. And so the three solutions, 3 cubic roots of 1 are e to the 0th, e to the I0 if you like, which is 1. Of course, 1 cubed is equal 1, we know that. Or another one is e to the 2, or I times 2 pi over 3. And also e to the negative I 2 pi over 3. These are the three possibilities. Let's just plot these in the Argand diagram. We're going to get a better feel for what's happening. So if we draw the complex plane here, real axis, real part of z, and the imaginary axis. Say this is 1 here. All three of these numbers are on what we call the unit circle, so they all have distance 1 from the origin. They all have modulus 1. So the first one here is 1. The second one has argument 2 pi over 3, so we would have an angle 2 pi over 3 here. So this is about where e to the I 2 pi over 3 would be. And the other one has an argument negative 2 pi over 3. Would have a negative angle down here. You can also note these two are complex conjugates, so the other one would be this one flipped over the real axis. And so this would be the other one. This angle is 2 pi over 3. This angle, negative 2 pi over 3. Right? And this is e to the negative I 2 pi over 3. So these are all the cube roots of 1. All right, and I'm going to look at one more example. We can also find square roots or other roots of other complex numbers. Let's find all the complex numbers that are square roots of I. All right, so we know that complex numbers are obtained by allowing there to be square roots of negative numbers. Let's say, what if we then want to take square roots of I? This is towards showing that the complex numbers are closed under taking square roots, which was the motivation I gave at the beginning. So we want to find the square roots of I. So that means we want to find complex numbers so that z squared equals I. Right, so once again, we use the exponential form for z. We have r to the I theta squared equals I. And I'll also write I in exponential form. So I has argument pi over 2. E to the I pi over 2. But like before, we can allow a multiple of 2 pi. And we still get I. So let's say pi over 2 plus 2 pi n, where n here is an integer. Okay, so we get r squared e to the I 2 theta equals e to the I pi over 2 plus 2 pi n. All right, so considering the modulus, well, we have the modulus on the left is r squared, on the right it is 1. So r squared equals 1. R has to be a positive real number, so that means the modulus has to be equal to 1. Okay, and then considering the argument, we have that 2 theta should be equal to pi over 2 plus 2 pi n. So pi over 2 plus some multiple of 2 pi. Let's divide by 2, and we get theta can be equal to pi over 4 plus a multiple of pi. All right, and so the solutions of this equation, z squared equals I r e to the I pi over 4. That's what you get when you take n equals 0. And then if we want to get another value where theta is between negative pi and pi, we might take n equal -1, and we would get e to the negative 3 pi over 4 times I. So if you subtract pi from pi over 4. All right, so these are the two solutions. Other solutions, the theta would differ by 2 pi and from one of these two. And so these are all of the solutions. If we plot them on the Argand diagram as in the previous example, we have here the Argand diagram, real part of z, imaginary part of z. Then we're going to have both of them have modulus 1, r equal 1. And so this one has argument pi over 4, and so it's right about here, e to the I pi over 4. The angle here would be pi over 4. That's a 45-degree angle with the positive real axis. And then this one would have an angle negative pi over 4. It differs by negative pi from the other one, so down here would be e to the negative 3 pi over 4i. So this angle here would be negative 3 pi over 4. And you can see that when you square either of these numbers, you get I, because remember, when you multiply a complex number by another complex number, you multiply the moduli together. They both have moduli 1, so you just get 1 again. And then you add the angles. So if you square e to the I pi over 4, you add pi over 4 plus pi over 4, you get pi over 2, and you go to I, the imaginary unit, here on the imaginary axis. So you double this angle pi over 4, you get to here. Right? And similarly, if you double negative 3 pi over 4, you come around again to the imaginary axis and get I when you square e to the negative 3 pi over 4 times I. Another thing to notice is that these two numbers are actually negatives of each other, so you could also write this as z equal e to the I pi over 4 or negative e to the I pi over 4 if you wanted. But the way I've written it, they are in their exponential form, right? So a positive real number times e to the I theta, where theta is between negative pi and pi. All right, so there's some examples using the exponential form for complex numbers. It's the end of this video. In the next video, I'm going to discuss using the exponential form again to do some integrals, so integration of complex exponentials.